Hello, it's Stat 135, Lecture 14. So last time we started doing hypothesis testing in the frequentist framework called the Neyman-Pearson paradigm. We start with a decision function, which is 1 if we reject the null and 0 if we accept the null. A simple hypothesis is when the null and alternative distribution is fully specified. Of course, we can have two types of errors. One, which is called alpha, is when we reject a null when the null is true. The p sub 0 means that we're talking about the null distribution. The type 2 error beta is when we accept the null when the alternative is true. Today we're going to talk about the likelihood ratio test, which is the gold star for simple hypotheses. We'll talk about the power of a test as well as p-value. So the likelihood ratio test, or LRT, we start with a test statistic, which is a function of your sample that leads you to a decision whether to reject or accept the null. And you usually choose a test statistic whose distribution you know. Let's take a look at an example. So suppose there are two coins. We have coin 0, which has p equals 0.5 for heads, and coin 1 has p equals 0.7 for heads. We don't know which one we have. We choose the null to be the status quo, which is that we have a fair coin, in other words, coin 0, and h1 is the alternative. So to test, we flip the coin 3 times. X is the number of heads in the 3 tosses. We make the following table. So, of course, we have 0, 1, 2, or 3 heads. And the null distribution, which is f sub 0 of x, we can find by the binomial formula for n is 3 and p is 0.5. The alternative distribution, f1 of x, is given by the binomial formula for n is 3, p is 0.7. And the likelihood ratio is the ratio of the null to the alternative distribution. So we can see that, for one thing, we would reject the null if of course, if x is very large, right? Because that would indicate that we have a p greater than 0.5 of getting heads. To say that we would reject when x is greater, let's say 3, for example, would be equivalent to saying that the likelihood ratio is small, namely like 0.364. And so we're going to find what we call a rejection region and an acceptance region, and this will be determined by alpha. So for a fixed alpha, the likelihood ratio test says reject the null hypothesis if lambda is less than c. And the cutoff c is a function of alpha, since alpha is the probability under the null that that lambda is less than c. And so, for example, if alpha is 0.5, we can see from looking at the second column that we can see that c is 1.984, because when lambda is less than that, the error is 0.125 plus 0.375, which is 0.5. So the likelihood ratio test is reject the null if lambda is less than 1.984, or equivalently reject the null if x is greater than 1. So values where we reject the null is called the rejection region. So now the power of a test is 1 minus beta, which you can write as we're going to reject the null when the alternative is true. So p sub 1 d of x equals 1. So in the previous example, when is it that, what is the power when, what's the probability under the alternative distribution that lambda is less than 1.984? Well, it's, you can see here it's 0.343 plus 0.411. So that's 0.784. So next we're going to look at an example where we're going to find the rejection region in the power of a LRT. So suppose under the null, a random variable x has a uniform distribution on 0, 1, and under the alternative, it has density 2x. So what is the likelihood ratio test at alpha equals 0.1 level of significance, and what's the power of the test? So it's helpful to make a picture of the null and the alternative hypothesis as a function of x, since we know what those are. So if we set alpha equal to 0.1, so we can see what the cutoff needs to be. So 0.1 is the probability under the null hypothesis that 1 over 2x is less than c, or equivalently that x is greater than 1 over 2c. So for one thing, you can see that the rejection region is going to be to the right, so to have the probability be 0.1, we can see that the threshold needs to be 1 over 2c. So in other words, 1 over 2c needs to be 0.9. So because of course from the picture you can see that under the null, the probability that x is greater than 0.9 is 0.1. So in other words, c is 1 over 1.8. So the likelihood ratio test says lambda is less than 1 over 1.8, or equivalently x is greater than 0.9. So now to find the power, so in a picture, the power is the area under the alternative to the right of 0.9. In other words, the area under the alternative above the rejection region, and that, just a very simple calculus, is 0.19. So the Neyman-Pearson lemma says that if the null and alternative are simple hypotheses and that the likelihood ratio test rejects the null with significance level alpha, then any other test for which the significance level is alpha has less power. So in other words, the likelihood ratio test is the most powerful test for a given level, alpha level. The book, please read the proof in the book. So the likelihood ratio test is the best that you can do for hypothesis testing of simple hypotheses. Finally, just give a quick example of a p-value. So p-value, a test statistics p-value is the probability it's as or more extreme than what you observed. So you reject the null if the p-value is less than alpha, since in this case the test statistic is in the rejection region. So your rejection region tells you what it means to be as or more extreme. So getting a point in your test statistic inside the rejection region, clearly the p-value will be less than alpha. Alpha is the area shown in red here. The p-value is the area shown in black. So suppose a test statistic T has the standard normal distribution. If the test rejects for a large absolute value of T, what's the p-value if you observe minus 1.5? Well, if the test rejects for a large absolute value of T, what does that mean? It means it rejects if the absolute value of T is greater than C for some positive c. In other words, t is greater than c or t is less than minus c. So we have a two-sided rejection region as shown here. So when computing the p-value is the probability under the null that t is less than minus 1.5 or t is greater than 1.5. So this you could just do a simple calculation knowing that the null distribution is standard normal, and we're good to go. Just note that if the LRT says reject for large negative values, then the p-value would be one-sided. In particular, we would reject on the left. Okay, that's it for today. See you on Wednesday.